everybody, and welcome back to integrating stuff. So far we have looked at U substitution as a way to get at an integral. If U substitution doesn't work and we have a product, we talked about integration by parts as a way to try to undo a product that didn't just come from a chain rule. Today we are going to focus on integrals that we're trying to do that are rational functions. So when I'm looking at an integral and I see a fraction, what do I do? Okay, so I'd like you to take a look at the two integrals that are here on the screen. The one on the left, the green one, two fractions. The one on the right, the purple one, is one fraction, of course. And I want you to take a moment and either integrate or tell me why you can't. Okay. So if we take a look at the integral on the left, the green one, it may not look like a whole lot of fun, but it is integrable, which is a word that I can never say, able to be integrated, because what we really have are just some 1 over u's, right? So I can actually take the 2, I'm going to break this into two integrals. I can take the 2 out, and I have a 1 over x, so that's just an ln of x. And then over here, I can take the 3 out, and I have a 1 over 2x minus 5, which isn't ready just yet, but I can get it there, right? So here, I just have 2 ln absolute value of x. Over here, I guess I don't want to do that yet. I've got a 1 over cloud or a 1 over u, so my du needs to be 2 dx. So if I put a 2 here, I need a 1/2 out here. So this ends up being 3/2 ln of 2x minus 5 plus c. Okay. Now again, I could point out to you that they could do all kinds of fun stuff with this, right? They could rewrite this as the ln of x squared. They could rewrite this as the natural log of 2x minus 5, but you would still need these to the 3/2. Then they, since this is an addition, they could put it together as a product. They could make it say the natural log of x squared times 2x minus 5 to the 3/2, like this, right? All of these along the way are true. So again, when it comes to natural logs, keep an eye out for that. Anytime you have an integral involving a fraction, this is going to be our first line of defense, right? See if you can fit it into a 1 over u du. It's the simplest. Hope it's a u substitution. All right. When you look over here at this purple integral, though, you probably notice things fall apart pretty quickly, right? If I try to fit it into a 1 over u du, that would mean that I have a 1 over 2x squared minus 5x, and then over here, this 7x minus 10 becomes part of my du. Now, it's so close, right? I need a 4x minus 5 over there. That's what I need. If this was an 8x minus 10, all I would have to do is pull a 1/2 out, and I'd have a 4x minus 5 sitting there. And it would be perfect. It would be a 1 over u du. But it's not. It's not perfect. And there's not really anything we can do here algebraically that's going to help. So I could break this into two fractions. But that also doesn't help, right? If I do that, how did that become that? Okay, if I do that, I need a 4x minus 5. Don't have it. I can adjust the 7, but I can't get the minus 5. And here again, I don't have the 4x minus 5. So this is kind of a mess. Okay. So sometimes we can fit a fraction or a rational function into a 1 over u du, and sometimes we can't. What I want to focus on today is when this happens. Right? If you can get it into a 1 over u du, awesome. If you can't, what are we going to do next? All right. So, what's interesting about these two integrals is that they're actually the same integral. So if you look at these two fractions right here, and you say, you know what, Algebra 2 was so much fun for me. It was the best mathematical year of my life. I'm going to take a moment and do some fraction addition, because that's what I like to do, right? I like to add rational functions. So if you do that, you take a common denominator, right? You take this and put them together to make a common denominator. And then we rewrite our numerator. So we get 2 times 2x minus 5, and we get 3 times x. If you simplify that out, you get 7x minus 10 on the top, and you have your old denominator. So even though these look really different, and we just said, oh, this one we can do no problem, this one, yeah, not so much, okay? They're the same fraction. So the fact is, there is conceivably algebra that could bring me from here to here, right? There's algebra that takes me from here to here. So there is algebra that's going to bring us back. Right? It's just not any algebra that we traditionally go, oh, I have an idea. Let's do this, right? Well, guess what? That's what we're going to start doing, okay? We need to figure out when we have an integral written like this, what we're going to do about it, right? It's not going to just pop out as a 1 over u du. So we need to get clever with our algebra. And that's all it is algebra, but we have to get clever with it. All right, so this process that we are going to use, that we are going to get clever with algebra, is called partial fraction decomposition, which sounds, I know, horrifying, right? It's really not that bad. It's a lot of syllables. It doesn't sound fun, but it really isn't that bad at all. All right, and again, it's all algebra. So basically what happens in this section is we do a bunch of algebra, and then we say, I wonder if I can do calculus now. It's sort of like with integration by parts, where we do that rewrite, and then we go, I wonder if I can do it now. We're going to do that again, except for partial fraction decomposition. The rewrite is all algebra. It doesn't involve any integrals or anything like that. Okay, so when you have a fraction, when you have a rational function and an integral, there's always 2 places I want you to look first before you start doing what I'm about to show you. Okay, the first thing, like we said, that you always check is to see if it's a 1 over u du. Is it a natural log? If you can fix it into a 1 over u with a du, or a 1 over cloud with a d cloud, then that integral is going to be the natural log of that u. Period, end of story. Easiest way to get it done, if it'll work for you. If that doesn't work, always check to see if it's an inverse trig. Okay? So for example, if you have something like 1 over 1 plus x squared, you may try to make that into a 1 over u du, and notice that you're missing an x. If that happens, take a pause and go, is that possibly an inverse trig? And it sure is. Okay? That's an inverse tangent. Those are ones you just have to have memorized, right? But that's kind of our second line of defense. If neither of those 2 things work, then we're going to see if we can do a partial fraction decomposition. Okay, so in order to do a partial fraction decomposition, you have to have a function that has a factorable denominator. Right? That has to be, you have to be able to rewrite your denominator as a product in order to do decomposition. Okay, so this is the most Algebra 2 intense section that there is, right? Because remember when you learned how to factor completely? All those factoring patterns. Here's a polynomial. Factor it until you can't factor it anymore. Difference of 2 squares, difference of 2 cubes, sum of 2 cubes, pulling out common factors, all of that stuff, right? That's what we have to be able to do to our denominator now. As soon as we see a rational function that isn't a u sub, isn't a trig function, first thing we're going to do is look into that denominator and say, well, is this factorable? Because if the denominator is factorable, we've got a chance. Okay. If the denominator is factorable, what we are going to do is we are going to break that fraction into a sum of smaller fractions. In other words, if I have a factorable denominator, I'm going to say, okay, well, here's what I'm going to assume. I'm going to assume that that product denominator came from other functions, and this denominator I'm looking at is a common denominator. And so I'm going to try to back it up and figure out what the original pieces were that came together to create that common denominator. I'm going to decompose that denominator. Right now, it's the whole common denominator. I want to break it back apart into the pieces that it came from. Okay, and again, that's just a little algebra process. We hope then that our simpler fractions, our pieces, we can individually integrate. That's the hope. Okay. All right, so A partial fraction decomposition is very simply the undoing of adding rational fractions, right? So if you added two rational functions, I want to pull them back apart again, right? It's the equivalent of saying, okay, I'm going to take 2 plus 3 and add it to get 5, and then somebody coming along and saying, I have a 5, how could you write that as a sum? So somebody might say, oh, I could write it as 1 plus 4. And somebody else might say, oh, I could write it as 2 plus 3, right? We're backing it up. We're looking at the sum. We want to break it into the pieces, the addends, the pieces that were added to give us that sum. Okay. All right. Couple things about that fraction. We said that it has to have a factorable denominator. There's one other key thing about the function that we're looking at that we have to always make sure is true. Usually it's already true. Okay. And that is that you have a proper fraction. So before you go factoring that denominator and going off on your way, you have to make sure you have a proper fraction. Now, when we're talking about numerical things, we know what that means, right? So in other words, if I have a 5 in my denominator, then I need my numerator, in order for this to be proper, to be less than 5, right? I mean, I guess it could be 5, but we want it to be 1, 2, 3, 4, something like that, right? If I have 6/5, that's not considered a proper fraction. Okay. When it comes to rational functions, we're not talking about necessarily numbers, we're talking about the order. Right. So if I have a rational function and there's an x squared polynomial down here, I need this to be either linear or x. I need it to be lower. I need my numerator to be lower order. Right? If I have an x to the third polynomial down here, then I need these numerators. I need this numerator to either just be numerical, first order, or second order. Okay? This is really, really important. If you don't start on this premise, then the whole method of partial fraction decomposition falls apart. You'll see why when we get to it, right? But you have to have a function that is in proper form. Okay. Now, if it's not in proper form, you learned something in Algebra 2 called polynomial long division. So in the same way that you would take 6/5 and say, okay, 5 into 6 goes one time and 1 left over, right? And rewrite it as a mixed number instead of an improper fraction. We can do that with rationals as well. Right? So if I have an x cubed something up here and an x squared something down here, I can divide these out and then get a remainder. The remainder should be proper. And we'll do one like that. But if it's like this, you got to stop, right? You don't want to go any further with something that's improper. Okay, and we already said that your denominator has to be factorable. Has to be factorable. The first step in partial fraction decomposition, other than making sure you have a proper fraction, is factoring the denominator. If you can't factor it, you can't go any further. Okay, so 3 integrals here. I want you to take a look at them and decide if you can, well, you know what, not even just is partial fraction decomposition appropriate, what method would you use here? Could you use partial fraction decomposition, or do you see another way to solve this integral? Okay, so go ahead and tell me what you would use for each one of these integrals. All right, so in the first one, I try to make it a 1 over u du, because I always try that first, right? If this is my cloud, I need a 2x. I have a 2, I don't have the x, right? So that's not going to work. That works down here. Look, oh, down here I have a cloud. Whoops. Same cloud. 2x is my u, or is my du. There it's sitting there. This is a nice u substitution. That's what I like. Okay. Up here, not so much. I'm missing the 2. Right? So the next question we ask ourselves is, well, could it be an inverse trig? Not this one, right? The inverse trigs are x squared plus 1. Now, look here. This does not jump out at you as an inverse trig, but it is. Okay? I could take the 2 out of here, and I can factor out the 4. So that would become like that. And then I have a u squared plus 1. This is an inverse tangent. It may not jump out at you as an inverse tangent, but that's what it is. Now, again, if you don't notice it's an inverse tangent, the next place you're going to go is partial fraction decomposition. is the denominator factorable? Here it is. Yes, this is factorable. So this could potentially be a partial fraction decomposition. Down here, this is not a factorable denominator. So now you're back to one of two things. If you didn't already notice, it's an inverse tangent. If it's not a u sub and you can't factor the denominator, it is either an inverse trig function, probably an inverse tangent, because that's the only one that doesn't have a square root on it, or this is an integral they're not expecting you to do. They want you to do something else. Okay. Only can I use partial fraction decomposition if it's a factorable denominator. Okay, so let's take a look here, adding rational functions. When we add, we know the steps, right? We find a common denominator, we put it back together to find the new numerator, right? Well, we don't want to add. No more adding. Now we want to decompose. In other words, instead of starting with two fractions and sticking them together, we're going to go the other way. I'm going to start with this, and I'm going to work my way back to here. Okay. First step is always going to be to factor the denominator. So notice, if this wasn't given to me factored, the first thing I would do is factor it. Okay. Once I have it factored, I don't necessarily know what my numerators were, but if this is my denominator, then I know this came from two fractions, and they had to have denominators of x plus 3 and x minus 2. They had to. Right? There's only one way to get this common denominator, and that's to have two fractions, one with a denominator of x plus 3 and one that had a denominator of x minus 2, because that's how we find common denominators. So from this, I can see that my original fractions, there were two, and those were their denominators, those pieces, right? So that's the decomposition part. Right? We are breaking this fraction into two fractions that we know it had to have come from. What we don't know is these numerators, right? And so step 3 is to be clever or strategic, right? Figure out what those numerators were. And we'll talk about a couple different ways to do it. Okay? Again, it's some algebra, right? But we're going to figure out what these original numerators were, and it's not terribly difficult. But the big leap here is figuring out that I must have had two fractions, and these must have been their denominators. Okay. Once we have them broken apart, we look at these and we say, can I integrate those? And look, I absolutely can. This is a natural log integral, and so is this. Home free. Okay, so I want to go through the process of partial fraction decomposition with you here. Bear with me, it's a lot of writing, and the first time we go through it, people are like, oh my God, is this going to be like the only question on the AP? This was so long, this took forever. And yes, it takes forever when I'm explaining it, but you'll notice when you start doing them on your own and you get used to them, they actually go pretty quickly. Okay, so I take a look at this thing, and don't forget, we're first going to check, is it a 1 over u du? Don't ever forget to check that. 1 over u du, well, if this is my u, 2x minus 5 is what I need up top. Not even close. Okay. It can't be an inverse trig because it's got this 5x in the middle, right? If it was like x squared plus 6, I smell an inverse trig, but it's not. It's a trinomial, right? So the next question we ask ourselves, do I have a factorable denominator? And I sure do. I can rewrite as x minus 3, x minus 2. Okay, so if I factor my denominator, I very quickly see that this thing came from two fractions. One of them had a denominator of x minus 3, and one of them had a denominator of x minus 2. Okay. What I do not know is what these numerators were. Okay. This is where the whole idea of proper fractions becomes super important, right? I do not know what these were, but I know one thing about them. My denominators are linear, which means these numerators had to have been just numerical, right? Because my original function, my original fraction is proper. I know the pieces it came from are proper. And that is so important, right? Because if I wasn't able to know for a fact that these pieces were proper, these numerators could be anything. They could be squared, cubed, to the 4th, to the 5th. I would have no idea. So the whole basis of partial fraction decomposition is that we have to work backwards and find those numerators. I have to be able to know for a fact that there's some restriction on what my numerator could have been. And I only have that guarantee if my original fraction was proper. So because I know that my original fraction was proper, I know these pieces have to be proper as well. So since this is linear, this fraction must have had a constant. I'm just going to put an a up there to hold the place. That's a constant, right? This fraction must have had a numerator that was constant, and I'm going to put a b up there. Partial fraction decomposition is one of the only places in math where you see them using like capital letters. I don't know why. It's one of the things that, like, when kids have learned it before and they see me do it again, they might not remember it until I write the a and the b, and then they're like, oh, that thing where you use the capital letters. I don't know why we do it. Okay, so look, here's what I know. I've got this original function. I know it breaks into two with these denominators, and I know my numerators must have been linear, or not linear, I'm sorry, numerical. Okay, so here's the silliness. We just decomposed it, right? We just took it apart. Let's put it back together again. I'm going to put it back together again, but my numerator is going to be now in terms of a and b. Okay, so if I put this back together again, x minus 3, minus 2. My numerator would be a times x minus 2 plus b times x minus 3. Okay? If I had these two fractions and I tried to combine them into one, which is what happened, right? My numerator would be this. Now, I don't know what a and b is. I don't know what they are yet. I do know, however, what this numerator ends up being. This numerator, I'm just going to recopy it. Whoops, sorry. This fraction ended up simplifying to 1 over x minus 3, x minus 2. This is where I started, right? So it broke into two fractions. I don't know what these numbers are. I know they're numbers, but I don't know what they are. I can recombine them, and I know for a fact that whatever this is equal to, whatever a and b are equal to, that whole mess better come out to 1, because that's what I started with. Okay, so I'm going to ignore these denominators for a minute and focus on just my numerators. What we know about fractions is if you have equal denominators, then you must have equal numerators, right? So I don't even really need to worry about my denominators right now. These are equal, so let's just focus on our numerators. All right. I know for a fact that a times x minus 2 plus b times x minus 3 has to equal 1. That has to be true. Okay? And it has to be true for all values of x. So what I could say to you is, look what you have here. You have two unknowns, right? So all we have to do is get two equations. We can solve a system, and we'll know what a and b are, right? And we can do that, right? I can say, okay, I'm going to pick when x is 0, right? So when x equals 0, this equation comes out to negative 2a minus 3b is equal to 1. All right. Then I'm going to say, you know what, I'm also going to do when x is equal to 1. When x is equal to 1, this comes out to negative a minus 2b is equal to 1. I've got two equations. I've got two unknowns. I can solve my system and figure out what a and b are. I'm not doing it. Right? This is too much work. Okay. So if you notice up here, I said be clever or strategic. Okay. You can do this. You can solve a system of equations every time you do a partial fraction You can solve a system of equations every single time you do a partial fraction decomposition, but you don't need to. Okay. And I'm going to show you why. We're going to be clever. We're going to be strategic. As soon as I recopy everything that I just wrote. Okay, so I know that a x minus 2 plus b x minus 3 has to equal 1. Right? That equation right there that I just wrote has to be true for all values of x. Okay. So I can pick any two values of x and use that to create two equations to solve for two unknowns. So since I can pick any value of x anything I want. Why not choose wisely? Make your life easy. So the way you choose wisely is by looking at this and going, you know what? If I just happen to choose that x is equal to 2, if I just happen to, this whole chunk goes away, right? If I just happen to decide, on a whim, that I want x to be 2, this turns into a times 0 plus b times -1 equals 1. And I don't have to solve a system because the a went out of the equation. I can get my b right off the bat, right? So I can say, okay, well, if -b is equal to 1, then b must be -1. I can also choose wisely again, right? If I need to fit, well, now that I know what b is, technically, it's much easier to find a, right? But I'm going to pick another x value, right? We need two unknowns. I need 2 equations. I'm going to pick another x value. What should I randomly choose? 2 made this piece go away. Where's my pen? 2 made this piece go away. The question is, what's going to make this piece go away? A 3. Okay, so if I choose x equals 3, if I just happen to, then I get that a times 1 plus b times 0 is equal to 1, and I can get straight at what a is. A has to be 1. Now, there's going to be, every once in a while, you can't make all but one variable disappear every once in a while. Okay? And if that happens, we have no choice but to just choose any random x value and solve a system of equations. But if you can, save yourself some time. Choose those wisely. You won't have to do too much work. Okay, so look, I know what a and b are now. I'm going to go right back up here. A has to be 1, b has to be -1. I figured it out. A little bit of algebra, a little bit of cleverness, a little bit of strategery. That's a George Bush word. And I know what a and b are. So, you may be asking yourself, are we done? No. We didn't do any calculus yet. We didn't do a stitch. Here's what I started with. I started with this integral. And I determined that I cannot do this integral as it sits. So I did a bunch of algebra, and I found out that I can rewrite this as this. I haven't done any calculus yet. What I've done is a little algebra rewrite. But thanks to my algebra rewrite, now I should be able to do my calculus pretty easily, right? If I break these into their own individual integrals, I have 1 over x minus 3. That's going to integrate to the ln of x minus 3. Minus, I have 1 over x minus 2. That's going to integrate to the ln of x minus 2. Done. Plus c. Easy peasy. 90% of the work on these is the decomposition. Once you get back from the decomposition, the integrals are usually pretty easy. Right? And there's a lot of natural log integrals here, as you can well imagine. Okay. I'm just going to say it again because I say it all the time. They could easily rewrite this. This is a subtraction, so they could rewrite it as a division. Like this. Just keep that in mind, right? If it's multiple choice, they usually do this. It's going to be pulled back together again. Okay. All right. So that is partial fraction decomposition. I have been talking for a half hour, so I'm going to stop. We will do some more integrals of partial fraction decomposition in class. Any questions that you have so far, pop them in the end of this video. I will see you soon.